this video, we would be learning about the mathematics of quantum mechanics. We would be starting this video in learning linear algebra in quantum mechanics, but before that we need to learn and understand why do we need linear algebra in quantum mechanics, why at all linear algebra is so important in quantum mechanics, and what are the essential areas of linear algebra which are related to quantum mechanics and how can we study with that. So primarily this video is where we are starting to learn linear algebra and how linear algebra is related to quantum mechanics and thereby understanding its importance. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to start this new video series on the mathematics of quantum mechanics, learning linear algebra. So before we start and go into the topics, let us see how we have planned today's video. So the topics that we have planned is that before doing anything, we need to first understand why do we need linear algebra at all, what is the requirement of linear algebra in quantum physics. For that we need to understand a little bit about what is called the Hilbert space, a little bit about measurement and observation. We will also do a very quick recap on complex numbers, what are scalars and vectors, and the notation of vector and its components. So first we need to understand why do we need to understand and learn linear algebra and why it is important in quantum physics. Now I would request the viewers that there will be certain advanced concepts which I have to touch base, because the root of mathematics of quantum mechanics is very formal, which deals and starts with linear algebra. So in case you are unable to grasp over those topics, don't worry, but this is just to give you an idea that why you are learning linear algebra and why it is important. Okay, so there is something which is called Hilbert space in quantum physics, and it is named after the famous German physicist David Hilbert. Now technically, if I call what is Hilbert space, it is a quantum system where every possible state of the system can be as represented by a vector, often infinite dimensional, in Hilbert space. Now let me explain a little bit what do I mean by that. Now what happens is that specifically in quantum mechanics, a state space is a complex Hilbert space in which each unit vector represents a different state that could come out of measurement. Each unit vector specifies a different dimension, so the number of dimensions in the Hilbert space depends on the system that we choose to describe. Now here it is mentioned that in quantum mechanics a state space is a complex Hilbert space. And what is a state space? In mathematics, Hilbert space actually allows generalizing the methods of linear algebra and calculus from finite dimensional Euclidean vector spaces to spaces that may be infinite dimension. So you see the first definition says that given a quantum system, every possible state of the system can be represented by a vector and which is infinite, and it is called Hilbert space. And the second one says that in quantum mechanics, a state space or the quantum state is a complex Hilbert space in which each unit vector represents a different state. That means that in mathematics, Hilbert space is a way of generalizing the methods that we learn in school level or high school level linear algebra, and it takes from finite to infinite. So here is the finite Euclidean space where we generally do all the mathematics and everything, and it extends here to infinite dimensional space. So the reason number one that we should understand linear algebra is that quantum mechanics deals a lot with Hilbert space, and because Hilbert space is an extension of the normal methods of linear algebra, so we should learn linear algebra. Reason number one, it deals with Hilbert space. Second, there is something which we all know is called a wave function. Now wave function, as you know, is denoted by this Greek letter psi, and it actually denotes the probability of finding the electron. Remember that it just denotes the probability. We cannot know whether the electron is at a specific position. We also know that the momentum operator that we call from the classical physics, it is not the momentum. It is something very complex. It is the operator associated with linear momentum. If you want to know really much more about what is momentum in quantum mechanics, you can go to my playlist in quantum mechanics and find out a dedicated video which deals only with the momentum, what it is in quantum physics. So what we can say that this linearity of the sets or of possible solution is true generally in quantum physics, as in the representation of physical variables by operators on the wave function. Remember that the operator momentum is an operator on the wave function. So the mathematical structure this describes the linear set of possible states, a linear set of states and sets of operator on those states is in fact a linear algebra of operators acting on a vector space. So you see the Schrodinger's equation highly depends on the linear algebra operators, and the mathematical structure which describes all those wave function, momentum, operator, all these are in fact linear algebra operators. So you get from here the second reason why you should learn linear algebra, because the entire wave function, the momentum operator, the Schrodinger time dependent or independent equation, all of them are basically operators and they are highly dependent on linear algebra. The third thing which comes is something which is called observable quantities. Now here is something I have just mentioned, a fictitious figure. It can be a stopwatch, it can be a thermometer or anything. These are basically what it is doing. They are measuring something, right? So we associate to every physical measurable quantity what is called a self-adjoint operator in the Hilbertson. What is a self-adjoint operator? Here it is. A self-adjoint operator on an infinite dimensional complex vector space is a linear map. So the self-adjoint operators have the special property. What is that? That their eigenvalues are real and that eigenvectors corresponding to different eigenvalues are basically orthogonal. So you see that these eigenvalues, eigenvectors are what? They are nothing but functions and operations of linear algebra. So when we are trying to measure something in quantum physics, we are associating at every physical measurable quantity a self-adjoint operator on a Hilbert space, and self-adjoint is basically an infinite dimensional complex vector space. So right at this moment, I hope you understand two very important concepts of mathematics which are required. One which we have already completed, that is complex number, complex plane, complex vectors, complex numbers and all those, and linear algebra which we are starting. So this is another very very pertinent example why linear algebra is required in quantum physics. Okay, we will come to another important thing which is called measurement. Now, what do I mean by measurement? Say, for example, let us assume that we have a system, any kind of an experiment, right? And we are measuring that. Now, immediately after measurement, regardless of what state the system was in beforehand, the system will be found in a state that is one of the eigenvectors of which the self-adjoint operators which we just discussed corresponds to the observable which we are measuring. So here it is. This experiment is turned to the next, which is a black and white, one of the eigenvectors of which self-adjoint operators correspond to the observable. Okay, so exactly which eigenvector the system will be, that depends when the system collapses, and it is definitely very much probabilistic in nature, and we know that the probabilistic nature can only be understood when the probabilities is squared, that is, we are trying to find the probability density. Now the numerical outcome of the measurement will be the eigenvalue corresponding to the eigenvector given at the first point. That is why we restricted our discussion to self-adjoint operators where the eigenvalues are guaranteed to be real. Now you see that when one measurement system is going to another which is an eigenvector, and we are trying to find it, the probability density and the eigenvalues of the self-adjoint operators are real. Again, these are all related to linear algebra. All are related to linear algebra. So this gives you a basic foundation stone before studying quantum physics, you should know that why linear algebra is important. So we get all those vector space and inner product, then Gram-Schmidt process, linear operators, adjoint operator, Hermitian operators, eigenket, eigenvalues, diagonalizing of Hermitian matrix. So all these are required in quantum physics, and these are heavily dependent on linear algebra. So until and unless you understand linear algebra, do the mathematics, get the basic foundation very strong, it is impossible to learn quantum physics. Also, I would like to point out that linear algebra is the study of vector spaces and linear maps between them. So it is in particular the backdrop of all the calculations that we are performing. When you solve an say for example, eigenvalue equation like the Schrodinger equation, you are doing linear algebra. When you expand a generic state as a superposition of eigenstates of some observable, you are doing linear algebra. When you are confident that such a set of eigenfunction even exist and that the corresponding eigenvalues are real, again you are doing linear algebra. It is because you have learned the spectral theorem for self-adjoint operator, which is a central in linear algebra. I mean to say, which is essential linear algebra in infinite dimensional spaces. So you see from here the standard formulation of quantum mechanics, whether you like it or not, is linear algebra, and that is why linear algebra is very, very important. So we have covered the first part of our video, that why linear algebra is important. I have given you certain examples, formulations, and understanding. So we now move to the next part of the video, but before that, a quick recap for those who have missed on my other video, which is called a complex numbers. It is there in my playlist, you can just go, but here is a quick recap. Considering these two numbers, z equals to a plus bi and w equals to c plus di, we know that I equal to square root of -1 is an imaginary number. Complex number multiplication is this, complex number addition is this, and we know complex conjugate given by a bar, or we can put a star. Also, we know that modulus of a complex number is given by this, the Euler's formula is given by this, the polar form is given by this, and the periodicity of a complex number is given by this. Here I would just like to bring the attention of the viewers is that I've also started a new series on complex analysis, and I have just given a video on how the imaginary and complex numbers are discovered. It is mentioned as the history of complex analysis. It's very interesting. You can go and check it out in my channel Physics for Students. Okay. So although we have introduced a new mathematical concept, the good part is that we have not introduced integral calculus or function analysis or something very complicated. We are essentially only using adding and multiplication. So this is a quick recap on my earlier video on complex numbers. Each of these Euler's formula, modulus, polar form are dealt in much details. You can just go and check out Mathematics of Quantum Mechanics series, where the complex part is discussed, I think, in 3 or 4 or 5 videos. Okay, so first we start with linear algebra for quantum mechanics, and the starting point of linear algebra is the concept of vectors. In high school physics, we have already seen that the concept as being nothing but a number and a direction. We would try to take a quick look on that. But before that, I would like to tell you something, that with the dawn of human civilization, before the advent of anything, what was very important is that human beings and we as people from science, we started to do one thing which is called measurement. We started measuring the speed of the wind, the velocity of the car, everything. It is central part is measurement. Now here is a 60 kilogram of rock, right? And we want to measure that it has got a mass. That's fine. Now if you take this rock and we take it in east, west, north, south direction, we know that the mass remains constant everywhere. If I'm standing here and my weight will always remains constant in all these 4 directions. That means we are dealing with something which requires no direction, and that is what is called a scalar. There's a quick recap, so you can skip on that part. What is a scalar? Everybody knows that. Now if I'm standing on ground, and if there is a force which is acting downwards, and the measurement of force is 10 Newton, because gravitational force is acting downwards, so we can say a force of 10 Newton is acting in the downwards direction. So for certain quantities, we require to join the direction along with the magnitude to describe them, and these are called vectors, taken from the Latin word viher, which means to carry. So a vector is the mathematical representation of a physical entity that may be characterized by size and direction. A scalar is the mathematical representation of a physical entity that is only characterized by magnitude. Nothing great, but just a quick recap in what is a scalar and what is a vector. Okay, in general, when we talk of vectors, it is denoted either by an arrow on the top, that is also a vector. It can be a letter which is bold. So when we type something with a bar at the bottom or bar at the top, these are also vectors. So we write x equals to vm, so the bold v is the vector. So the magnitude or length is written as this. Unit vector, that means a vector whose length is just 1, is written as this. And a vector may be located in a rectangular coordinate system, which is given by angular brackets, something lists by this. And an alternative way of writing is something like 1001. I can write v equals to 6i and 3j. Remember, those simple small hats on the top means that these are unit vectors which has got a length of 1. So a vector with a fixed initial, that means it starts at some point and terminates at some point, it is called a bound vector. And since a position vector does have a defined starting point, it is called a bound vector. So if it moves in the opposite direction as shown here, it is called negative. Right? And free vectors, there are certain things called free vectors, which refers neither a point nor a line, and it can move around freely. So it has a fixed magnitude and a direction, so you can move free a vector anywhere, and it looks something like this. Just also note to all the viewers is that I have given a very detailed analysis and understanding of 13 type of vectors in my new series, which is called Vectors and Tensor, which I have just posted yesterday. You can go to my videos on physics for students and check out the video which is called Vectors and Tensor, where I have spoken about tensors as well as vectors and a little bit more about the different types of vectors. Okay. So in general, by representation, if I called a graph or something, is represented as this. But sometimes, you know, it also shows like this. Multiple of arrows going here and there and here and there. So these are called vector field, which we all know is issues a vector to each point in space, and thus allowing us to represent the physical occurrences in our everyday life. For example, the merry-go-round, if it goes around, if I need to mention the space or the speed of the merry-go-round, I have to use a vector field. Also the sloshing of your morning cup. It illustrates the vector field. So whenever we get multiple lines and we are trying to mention some kind of a fluid or a movement of multiple forces, it is called use this, and it is called vector field. Okay, so the starting point is that from the mathematical perspective, vectors is something you can say that it is just stacking numbers together. For example, this one, it is a column vector, and if I say this one, it is a row vector, right? So unless otherwise specified, when we refer to a vector, we generally call it as a column vector. So definition of a vector comes from here. Vector is a column number. Any numbers, even complex, the amount of numbers is referred to is known as the dimension. So here v equals to v1, v2. This is just a kind of a definition. It's a two-dimensional vector. An n-dimensional vector can take form of this, right? Where v1 is referred to as the first component of the vector v, v2 is referred to the second component, v3, v4, and so on. It goes up to vn. Notice this is the arrow. This is a widely accepted convention to stress the fact that v refers to a vector. And if we consider the n-dimensional real vectors, that is v1 to v2, then we can say the vectors lie on Rn. And if we consider the complex vectors of n dimension, then we call it lies on Cn. So these are just, you know, mathematical symbols to mention that which one lies in real and in complex numbers. Okay, so even if you have never explicitly learned about vectors, for example, you have already seen them. For example, this one, a two-dimensional vector of real numbers, it is absolutely similar to that of the Cartesian coordinates, right? So it is 1 and 2. So it is also the mathematical way of representing the points on the Cartesian plane that you would end up to if you're starting from the origin, then move 1 along the x-axis and then 2 along the y-axis. It is also the mathematical way of representing the point on a Cartesian plane, right? A three-dimensional vector of real numbers is analogous to the spatial coordinates in three-dimensional plane. You can always think of vectors with n numbers as something which is called a hyperspace. So I've just given a fictitious figure. This has nothing to do with hyperspace. Okay, so now that we have understood the vectors, we have understood the notation of vectors, we have also understood the row and the column, etc. look like. Now, how about doing a little bit of operation on vectors? And what do I mean by operation is that let us find out what do we mean by vector and its components. Now, essentially, if you take this vector, this black one, then sometime it becomes important for mathematics and other areas of physics to divide a vector or to divide a particular vector into different components. Why? Things will become soon clear. We need arithmetic, addition, multiplication, etc. So taken this vector, if I take 4 points along the green and then further 4 points with this blue arrow and then further 4 points with the purple arrow, I can say this vector is made up of 4 units of green arrow plus 4 units of blue arrow plus 4 units of purple arrow. So the components of a vector are the pieces that can be used to make up a vector. The components vector helps us in the division of a given vector into parts that are oriented in different direction, and it helps to facilitate the execution of numerous arithmetic operators involving vectors. So we have understood that we can divide a vector into small parts and it somehow helps in our doing arithmetic, etc. But that is also not. What if we change the, so here is one vector which is in a type of a coordinate system, and we from here you see I'm trying to join this, right? So this is two black vectors followed by one red vector and 2 blue vectors. So here I can say this is made of 2 units of black vector, 1 unit of red vector and 2 units of blue vector. Now, what I was trying to tell a few seconds earlier is that the components of a vector is not only that it helps in addition and dividing the vector into components, but about when we move from one particular coordinate system to another. So what if this coordinate system of xy, which is a typical Cartesian coordinate system, is now changed to this? So you see I have just changed it, right? So still we can make up this vector. So how do we make up? So you see this is how it happens. So if we now add it unit by unit, it will be 2 units of black vector. Here it is changed from 1 unit to 3 units of red vector followed by 1 unit of blue vector. So what has happened very importantly is that the vector remains the same. That is called the invariant nature of vector, whereas the components of the vector changes. This is central. This is the absolute foundation, I would say foundational concept in understanding vectors. We use vectors from one coordinate system to another. We see that the vector will remain the same. Otherwise, how will we do the measurement? But the components changes and it happens more in other coordinate system. Similarly, we can just take this kind of an example, a cube, and I am drawing those lines. It's just an illustration, nothing mathematical, and I am assigning these reflection of vectors, that is the components of the vectors, with these black arrows over the blue arrow, and I mention xi for this plane, yj for this plane, and zk for the z plane. And I can always say that OA, that is the long one along the x-axis, is made up of xi, that is the unit vector, OB, that moves along the r, that is the m-axis, is made of yj, and OC is made up of zk. So what I can say is that r, that is the radial vector, is made up of OM, which is again made up of small 3 vectors, xi plus yj plus zk. So that is the components of vector. Don't worry, we will be doing a lot of mathematics on components of vector in the coming video. That's all for today's video. We just started. We have understood what are the components of a vector. Why do we need linear algebra? A little bit about revision on complex numbers and what is a vector and how the column and the row vectors look like. We will be continuing this in the next part of our video, and the next part of the video will deal with vector addition, parallelogram technique and vector multiplication. So now we are dealing with the linear algebra of quantum mechanics, and each and every video will concentrate on the linear algebra part. And now that we have understood why linear algebra is important, we find a lot of motivation to learn that, isn't it? Please let me know your views and opinions in the comment box. Please subscribe to my channel Physics for Students and click on the bell icon and click on the all notification so that you do not miss out on any video or any updates from Physics for Students. That's all for today's video. I will be waiting for your comment, and I will be continuing this series of linear algebra for quantum mechanics further one by one. Do let me know your comments. Keep safe, stay happy, learn physics and mathematics. I will be back with another video. Till then, goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.